So again, here we are. Let me remind you that as we wrap up our lecture for tonight, we're going to be entering into spring break. All right. And there are not going to be any assignments due after tomorrow. So tomorrow you have your homework for acids and bases that is due. There's nothing due over the spring break. And I hope you take the time to maybe rest a little bit, catch up with work, with your homeworks, with your assignments, not just for my class, but for other classes you might be taking. Uh, guys, I know this is a difficult time, and I am very proud of you and the effort you're putting in. And it's been really, I feel honored to be able to share these things with you and to see how you've progressed. And I hope you don't, you don't quit, that you keep going, because I'm here for you. I put an announcement today in Canvas, and it's very important that you download that document that's in there, because it has some very, very important updated information about grading and about due dates and dropping class and all that kind of stuff that you guys always ask about. So make sure you download that and read that. And if you have any questions about procedures, unfortunately, I'm not the best person to ask, because I'm not very familiar with all of the procedures. So I would recommend that you contact either the counseling department or the admissions and records, okay? Just be aware, like I said in that announcement, that this class has the option of switching from a letter grade to a pass, no pass state. So, if that's what you're considering, you need to explore your options and make sure that you get the information right, as depending on what kind of college you're trying to transfer to and whether that'll work or not. Okay, so I just wanted to say that. Again, over the break, please check your grade book to make sure that everything jives, that everything is consistent, that there's no discrepancies between what's on the grade book and what you believe that you have turned in. All right. And again, no exams are scheduled yet, nor before nor after spring break. I had to work that out, and I still don't have a consensus on that from the rest of the faculty. So we will let you know. So don't worry about that. Don't worry. You will get evaluated one way or another. All right. So over the spring break, of course, I'll be working out some of our activities that we're going to be doing after spring break. One of the things that I would like to do is perhaps be able to make these sessions a little more interactive, kind of like a real classroom. I know that most of you come in with your microphones muted and no video. I guess you're a little shy, and that's fine, no problem. So please, be aware of that I'm thinking about that. Okay, I'm just thinking about it. Okay, guys, let's go ahead and wrap up our study that we had before about acids and bases. And I believe this is where we left off, right? We had talked about the process of different salts dissolving in water and generating solutions that are actually acidic or basic. And we read the different kinds of things. Now, there's other substances that can also alter the acidity of water when they get dissolved. So I'm showing you a picture here of what happens when you put dry ice in water. Now, what we've done here is on the left is we have what's called an indicator, right? So an indicator is essentially a substance that changes color in the presence of acid or base. And as you can see, this indicator, when you put this little piece of, this little piece of dry ice in there, it turns yellow, indicating that it's become acidic. So let's go to our thing over here. Okay, so please go to your window, the frame that has this, and make sure you pin that page there, a screen, so we can go over and explain to you what's going on here. Okay, so essentially dry ice, what dry ice is actually CO2, right? Solid. When you put it in water, you know what, let me get a different marker here. This is my pen. Let's get the marker here. Some of the carbon dioxide actually dissolves, very little of it. As you remember from Chem 1A, gases are not very soluble in water. But what happens is that the CO2 in water will interact with the water itself and establish a very weak acid equilibrium that produces this substance H2CO3, which is called carbonic acid. And so carbonic acid is a weak acid, and it will ionize into, of course, hydrogen ions and the bicarbonate ion. And as you can see, this is what is responsible for the water becoming an acidic solution. Now, here's what's interesting. If you take water from the tap, for example, or even distilled water that's been sitting, on your bench top for a few minutes, it also is acidic if you measure the pH. And the reason is that carbon dioxide in the air, oh, sorry, I should have explained that this was reversible here. Sorry about that. Carbon dioxide in the air, I think I lost my video here. Oh, did I get a bad connection here? Did I lose my connection? Hello, hello. Okay. Hold on a second. I seem to have lost my screen here. Sorry, guys, I seem to have had a glitch in the matrix here. I don't know what happened. Okay, there I am again. I hope everybody's got me. Back to our screen here. I'm sorry about that. I don't know what happened. It seems like I got disconnected briefly. The recording is still going on, so hopefully I didn't lose you. Again, if you get for some reason bumped off of the meeting and you come back in, you might end up back in the waiting room. So something will flash out here and let me know. Also be aware that when I go to the screen sharing with the PowerPoint, I cannot see the chat room. So if you put any messages out there, I'll see a flashing that something's in there, but I can't access it. So please wait till I come back, or rather maybe just unmute your phone and just ask me by your voice, okay? All right, so what I was saying is that the carbon dioxide in the air by itself is capable of giving us this carbon dioxide dissolved in water, which turns it acidic, just like if we had solid dry ice being dissolved in there, okay? Now, that's an interesting thing. So if you were in the lab, one of the things that would happen is that when we do the experiment with pH measurements, some students get surprised that when they measure the pH of water, it comes out acidic. And that's because of the presence of the carbon dioxide. Okay, let's go back to our PowerPoint here where we were. Okay, here we go again. All right, here we go again. Let's get this guy out of the way. All right, so let's consider then what we have defined as an acid. We're going to wrap things up here. So we said that originally the definition of an acid came from Arrhenius, and the way he presented it was what happens when you put the substance in water. And the definition was a substance that produces hydrogen ions in water, or rather hydronium ion, is considered an Arrhenius acid. Then we expanded the definition so that we wouldn't have to require necessarily that the substance be in water. And we define a Bronsted acid as a proton donor. Well, guess what? We have a third perspective about what an acid is, and it is called a Lewis acid. And in this case, we're going to talk not about protons being donated, but about electrons being accepted. All right, electrons being accepted. So let's think back about our standard neutralization reaction, right? A Lewis base will donate a pair of electrons. Okay, so here we have, let's say that I have HCl, which generates protons in solution, and sodium hydroxide, which generates hydroxide ions. All right, so what we're going to say is not that the acid is donating a hydrogen to the hydroxide, but actually that the oxygen in that hydroxide ion is going to donate a pair of electrons to that proton. And therefore, because the proton is accepting a pair of electrons, we consider it an acid from the Lewis perspective. And because the hydroxide ion is donating a pair of electrons, we consider it a base. All right. Let's look at the same example with ammonia. Let's say that now I react, let's say HCl with ammonia. So I have my hydrogen ions, and then I have my ammonia molecule. Remember that it has a lone pair on the nitrogen. And we're going to say that what happens here is that the nitrogen donates a pair of electrons to that proton to produce the ammonium ion. Again, in this perspective, we think of the proton as being the actual acid because it's accepting a pair of electrons. And we think of the ammonia as a base, not because it generates hydroxide ions, not because it accepts a proton, but because it donates a pair of electrons. Now, when we talk about this idea of donating a pair of electrons, it might be easy to get confused with oxidation reduction reactions, all right? So let's come over here to our screen again, into our document camera. And the reason I want to do this is I want to prove to you that there is no redox process here. Remember, when there is a oxidation reduction, there is a change in the oxidation number of the compound, or the elements in the compound. So let's look at ammonia. And let's look at its product, which is the ammonium ion. Let's calculate the oxidation states here. Okay, hydrogen is always +1, so we have 3 at +1. And then you have ammonia at who knows what, let's call it X. I'm sorry, not ammonia, nitrogen, I'm sorry. And that would add up to the total charge here, which is 0. So that means that in this compound, nitrogen has an oxidation state of -3. Now let's look at ammonium. In the ammonium ion, you have 4 hydrogens, each of them at +1, and 1 ammonia. I'm sorry, I keep saying ammonia. 1 nitrogen, I'm sorry, 1 nitrogen at an unknown value. Now in this case, the total charge of the unit is +1. So again, in this case, X is also equal to -3. In other words, there is no change in the oxidation state. So when we say, you know, a Lewis base is donating a pair of electrons, right? So a Lewis acid will accept, Lewis base will donate. We are not saying that the electrons are being transferred to the other substance in the way that a redox reaction happens. It just means that they are going to be becoming a part of a chemical bond, okay? So that's very important. So let's come back here to our PowerPoint again. There we go. So let's look at an example here that might illustrate this. Compounds made of boron are typically very good at as Lewis acids. All right. So let me see if I can get us here. There we go. So this is a compound, has different names. It's sometimes called trifluoroboron or trifluoroborane. I mean, it has different names in it. Usually compounds of boron tend to not have a very strict set of rules for the naming. Okay, so let's say I react that with ammonia again. All right, so remember, the deal here is that the ammonia as a Lewis base will transfer or donate, not transfer, sorry, donate a pair of electrons to the boron, which is depleted because it only has 2, 4, 6 electrons around it. And you end up forming something that looks like this. All right. So in this case, the boron trifluoride reacts with ammonia, which would be the base, to form a substance that is sometimes called an adduct. And the idea here is the reason why this is sometimes not called merely a molecular compound or whatever is because both of the electrons in that bond there, right? Both of the electrons in here came from the nitrogen in the ammonia. That's the whole idea. So in other words, notice that in this case, there has been no donation or acceptance of protons. Therefore, a Lewis acid-base reaction is kind of outside the box with respect to our, more familiar Bronsted acid and base. All right. Believe it or not, you have been experiencing or learning about these kinds of reactions with all of these analysis that you've done on cations. Remember this one you did, well, probably don't remember, but you did an experiment where you did the equilibrium of between iron 3 ions and the thiocyanate ion. Remember that? So when we did that, what we looked for was the formation of a complex ion. And hopefully you remember that the idea here was that this was a red, right? It made the solution red, if you remember that. And so this process of forming these complex ions, and you've seen quite a few of them as we've gone through those labs, that is essentially a Lewis acid, Lewis base type of reaction. Okay, so that's what I wanted to say, and I'm gonna leave it there as far as this is concerned. We are gonna revisit this idea of the Lewis acids and bases in our last topic of the semester, because we're going to be studying the formation of these complex ions with a lot more detail. So keep that on file, keep it, stowed away so you can pull it out of your memory, in a few weeks when we come back and revisit this topic. All right? Okay, cool. Well, let me come back here. All right, let's come back here and let me ask if there are any questions about any of this. Again, let me check the chat room here, see if anybody had any questions there. Right now, I'm not seeing anything, probably because I lost you when I got disconnected. But if you have any questions, just let me know. We're going to be switching over to our other topic, will be chapter 16. So let me take a couple seconds to pull up my files for that. And in the meantime, if you can look up your PowerPoint notes for that topic, okay? All right, I'll be right back. Okay, I'll be right back. Just trying to get this thing to behave here. It's not behaving. Okay, sorry about that. That took a lot longer than I expected. Sarah, no, I don't prefer for you to have your camera on. Don't worry, I'm not trying to force that on you. I'm just trying to say that, after spring break, I may want to make this a little more interactive. So For now, it's fine. Don't worry about it. I'm just trying to come up with ideas. This is as new for me as it is for you. Okay, guys? So thanks for your patience and your support. Okay, let's go ahead and come back here. So we have basically covered a lot of material here with acids and bases, and I hope that the homework problems are good practice for you, as well as the ones that we've done here over the spring break. I encourage you to, when we come back, to review a little bit of what we're going to be talking about now, because we're going to pick it up right there. And I know sometimes our memory is not that good always. So even for young people like you, right? Sorry about that. I'm being funny here. Okay, anyway, let's do this. Let me take our new set of notes here. And let's do actually, you know what? Let's do a practice exercise here. I'm going to have a practice exercise. I like that. Let's do this. Okay. We're going to be talking about aqueous ionic equilibrium. And this is the one where we're going to be tackling some of the these precipitation reactions that you've been looking at in your lab activities, and also this titration and formation of complex ions and stuff like that. All right. So let's go ahead and move on. All right. So let's do this. Let me have you guys work this exercise out. What is the pH of a solution containing 0.30 molar formic acid? And there's the equilibrium. Oops. Hello, Dr. DA. Do they give you the Ka here? Let's see. I think they gave you this, right? In your handout. You know what we need? We need the Ka, right? So let's go ahead and get started with our ice table, right? So the first thing you do is you set up your ice table. Let me give you a few seconds to work that out. You should be masters at this by now, right? So let me give you a few seconds. I want you to work on it. If you have any questions, just unmute your microphone and let me know. All right. We're good. Okay, so let's get started. So what are our initial conditions? Well, we have 0.30 molar of the formic acid, and then we have none of the ionization products. We're going to have a change. Again, I'm going to use the letter Y to represent. Oh, look at, they use X in this one. Okay, we'll use X then. All right. And so at equilibrium, we have these concentrations of our species. Now, we need a value for Ka. And that's it. Wait, where did you get that, Dr. DA? Oh, I'm glad you asked. Let's go back here to our textbook. All right. Let's look at our textbook here. Okay, here it is. Top hat. Remember that at the bottom of all the chapters, before you hit the solutions pages, there's a series of appendices, and you can go in here, and one of them has Ka values. So we can click on that to open this window. And here we go. We can look for formic acid, formic acid, formic acid. Anybody see it there? There it is, right at the top, formic acid. Notice they wrote it a little different than the way I wrote it. 1.8 times 10 to the negative 4. Okay, so this is probably the place where you can go to find these values if the question that you're dealing with does not provide them for you. All right. Okay, so let's go back to our problem here that we were doing. And here we go. So again, this will be the product of the ionization chemicals divided by the concentration of the unionized acid. So that'd be x squared over 0.30 minus x. And as usual, because of the small value of Ka, right? Because of the small value of Ka, oops, sorry guys. I can't find my highlighter here. Oh, there you go. There's my highlighter. Because of the small value of Ka, we are going to assume that it's safe to do an approximation here, and that the level of ionization of our acid is very small compared to its initial concentration. So now all we have to do is solve for x. I'm going to skip the math here. By now you guys should be pretty well versed in this. And the result we're going to get is 7.3 times 10 to the negative 3. And that is essentially the concentration of hydrogen ions, right? So pH is minus the log of that. And again, because the input number has 2 sig figs, my pH needs to have 2 decimal places. Several of you guys made that mistake in your quiz. You rounded as if the number on the left of the decimal period of the pH counted as a sig fig, and we explained that already. No, it doesn't. The sig figs are counted for pH, or logarithmic amounts, only by the digits to the right of the decimal period. Okay? Now, let's ask this question. What would happen if instead of having just formic acid, I come in and I add a salt that contains the conjugate base, which is the formate? What happens then? Well, we're going to talk about a phenomenon that is called the common ion effect. This is a shift in equilibrium that's caused when you add a compound that has an ion in common with the dissolved substance. Essentially, the common ion effect is a, kind of like a perspective or a version of, or an example of the Le Chatelier principle, right? So what happens is the presence of the common ion essentially suppresses the ionization of the original weak acid or weak base. So let's consider the example I just gave, okay? Let's say I have a mixture of HCOONA, that's sodium formate, and then formic acid, which is a weak acid. The salt itself is a strong electrolyte. In other words, it's going to completely dissociate and give me these ions of formate. The acid itself undergoes an reversible ionization into protons and formate ions. But here's the thing. Notice that we have a common ion here. So essentially what is happening is the presence of the salt increases the concentration of that formate ion, which means that according to the Le Chatelier principle, what's going to happen is this equilibrium is going to be shifted towards the left. In other words, towards the unionized acid. And so as a consequence, the concentration of hydrogen ions is going to decrease. So again, we increased that, we decrease this, and as a result, the pH of the solution becomes higher. In other words, becomes less acidic. All right. Now, I'm going to play with this, and then we're going to do an example, because I guess you're thinking, okay, the thing to do right now is let's do a little example here. Guess what? Let's do something first. I'm going to do an interesting derivation here. All right. Let's consider a generic mixture of a generic weak acid and its salt. Again, sodium, whatever, with the weak acid H, whatever. Okay. Again, just like in the example we saw, the salt will completely dissociate, and the acid will partially ionize, right? Don't forget, the process for the salt is just complete, 100%. The process for the acid is not. Now remember that for the acid, we have an expression of Ka. I'm going to take that expression of Ka and I'm going to rearrange it, okay? I am going to bring the hydrogen ions on one side, and I'm going to move the Ka to the other side, okay? So I'm going to do a little algebra magic here and rearrange that into this, all right? So all I did was I rearranged that into that. If you have any problems with what I did there, just ask me, okay? Trust me, it works. It's just algebra. All right, let's go. I'm going to now take the negative of the logarithm on both sides. Now remember, when you take the logarithm of a ratio, of a fraction, it's taking the log of the top minus the log of the rest. But simply said, we can rearrange this to look like this. I have minus the log of the hydrogen concentration equals minus the log of Ka minus the log of HA over A minus. I don't like so many negatives, so I'm going to switch minus the log of HA over A minus. I'm going to switch that fraction. Essentially, I'm going to multiply. I'm going to make the reciprocal of that and multiply it minus 1 on the outside of that log and turn that into positive. Notice that what I did here was I kind of reversed how that ratio was expressed. Again, this is all fair and square algebra. It can be done. It's doable. It's legal. And now I'm going to look at these two expressions here. Minus the log of H plus, what is that? That's right, that's the pH, right? So let's say that minus the log of Ka, I'm going to turn that into a property. I'm going to call it the pK, and that'll be minus the log of Ka. So the pK is analogous to the pH, except that what you're putting inside is actually the equilibrium constant, the Ka for that acid, instead of the actual hydrogen ion concentration. So let me substitute those in there and say that this equation is now pH equals pK plus the log of the base over the acid. And this is called the Henderson-Hasselbalch equation, all right? Essentially, it says that if you have a mixture of a weak acid and a salt that contains its conjugate base, you are going to have the pH is going to be the pK plus the log of the concentration of the base over the concentration of the acid. All right. Notice that if the concentrations of base and acid are the same, then that means that that second term is going to be the log of 1, which is 0. In other words, the pH will be equal to the pK. So depending on the relative ratios of base and acid, the pH of this solution will be either higher than, equal to, or less than the pK. And of course, the pK we obtain by finding what the ionization constant is for that acid and then calculating the minus the log of it. Now, why is this significant? Well, because this is the secret to forming what is called a buffer solution. So let's do this now. Let's go back to our problem that we had here, all right? And let's consider, I'm going to come back here to our other screen. And let's put this guy in here. All right. And if you don't mind, please pinning this video in there. This is the problem that we're just talking about. And that's not it. I'm sorry. I had the wrong one in there. Hold on. Okay. I continue to have this problem where I am losing things and I don't understand why. Hey, let's just, oops, and I lost the paper now on top of that. Okay, this is very, very embarrassing right now. I can't seem to find the paper that I was supposed to put in here. I guess I printed the wrong one. Okay, let's just get a blank piece of paper. Let's just do it like that. Sorry, guys. I'm very, very sorry about this. It's very embarrassing. Okay, where were we? We were trying to see what was the... Okay, so let's write it out here. We're looking for what is the pH of solution, and it has 0.30 molar formic acid and 0.52 molar potassium, formate. All right. So remember, before we did this one, we had a 0.30 molar solution of HCOOH, right? Now we have the presence of this guy here. So let's go ahead and consider this is a mixture of a weak acid and its conjugate base. So let's write out what's going to happen here. So the acid HCOOH will ionize into hydrogen ions and formate ions. Again, notice that the hydrogen that was connected to oxygen, that's the one that gets ionized out, right? The other one is connected to the carbon. That one is not acidic. So let's do our ice, right? Ice table. We're going to talk about molarities here. So we start out with 0.30 molar here. And this guy is 0. And this guy is 0. No, it's not 0. That's the whole point. This guy is starting at 0.52 molar. That's the point here, all right? So we're going to have a change in moles per liter. So at the end of the process, we have these concentrations of these different species. All right? So let's go back to our PowerPoint. I'm going to walk us back through that. All right. So we said that when we write out the ice table here, our formate, our conjugate base, starts at 0.52. And then we have our changes. And again, sorry, I borrowed this from somebody else and they use X instead of Y. But there we go. All right. So remember that now, because we have an initial concentration of this ion, this equilibrium is going to be shifted back towards the left. In other words, the presence of that base in there creates a Le Chatelier effect of shifting the equilibrium. In other words, suppressing the ionization of the acid. So to solve this, we're going to do the following. We're going to use the Henderson-Hasselbalch equation we just derived, right? Remember, it's pK plus the log of base over the acid. Now let's see what these concentrations are. First of all, concentration of the acid, 0.30 minus X. You know what? Remember what we just said. This ionization is so suppressed that very little of the acid is going to ionize, much less than the previous example where there was no conjugate base present. And because that is so small, in the same way, very little extra formate is going to be forming here. Okay, very little conjugate base. So we're going to make the approximation here, as we do in all these problems where we have acid and its conjugate base. And then we're going to fill things in. Now, we have to, again, find out what is the Ka of formic acid. But remember, we did it in the previous problem. It was 1.8 times 10 to the negative 4. So what is the pK of that? Right, the Ka is 1.8 times 10 to the negative 4. So the pK is minus the log of that, 3.74. Again, don't forget, if this guy has 2 sig figs, this one has 2 decimal places. Right? And now we're going to put these numbers into the Henderson-Hasselbalch equation. Let me give you a few seconds to catch up. Let me know if you have any questions about what we've done so far. Okay, again, reviewing. The point here is that we don't start with the conjugate base at 0 molar. It starts at some kind of value. We apply the Henderson-Hasselbalch equation. We assume that the changes in molarities are negligible. We calculate pK. We may have to look up the K of this acid. And now we're going to put the numbers in. So pH will be pK, which is 3.74, plus the log of base over acid. So that'll be 0.52 over 0.30. You can already tell that because that value of the log is bigger than 1, that means the log is going to be a positive number, which means the pH is going to be higher than the value of pK, and that value is 3.98. Remember, in the previous example that we did at the beginning, where we had just the formic acid, right? Remember what the pH was? pH was like 2.13 or something like that, 2.1 something. So the presence of the base suppressed the ionization of the acid and therefore caused the pH to increase slightly. Actually, it's not slightly. This is more than a tenfold increase in concentration of ions. Okay. All right. Let me give you a few more seconds to catch up. Let me know if you have any questions. All righty. Okay. So let me see if there's any questions so far about what we talked about. Anything, you can either unmute your phone and ask, or you can put it on the chat box there. I have it open again, finally. No? Okay, well, why don't you think about it, and we're gonna take a 10-minute break, all right? 10-minute break. And when we come back, we're gonna develop this Henderson-Hasselbalch equation into the formula for dealing with a type of substance or system that's called a buffer system, okay? So let's take a 10-minute break. We are going to stop the recording, pause the recording for a moment here. Okay, we are back. Thanks for hanging around and waiting a little bit, all right? While we were gone, some good friends of ours brought us dinner. That's awesome, man. Very, very nice gesture. And of course, they left it at the door, told us about it, and kept proper distancing, right? That's very good. Okay, let's continue our study here. Okay, so where we're at is the following. Let's go back to our PowerPoint here. This last thing that we did here was we realized that when you have a conjugate base present along with the weak acid, particularly if they're both in, sufficiently high concentration, half molar, something like that, or somewhere in that range, what happens is that you establish an equilibrium that revolves around this pK value. And as we're going to see, it's very difficult to alter that equilibrium now because of the Le Chatelier principle. And that is what allows us to build what is called a buffer solution, sort of like the ones that you see in different kinds of IV bags and stuff like that. It's a solution where you have a weak acid or base and its conjugate. Typically, I like to speak of it as saying it's a weak acid and a salt of the weak acid, because the salt of the weak acid contains the conjugate base, all right? And the idea is both must be present, otherwise it doesn't work. Now, why do we call it a buffer? We call it a buffer because it has the ability to resist changes in pH when we add, small amounts of either acid or base, in extra. And by that, I mean like a strong acid or base. So let's look, for example, at this. Consider again the, let's say this would be acetic acid and sodium acetate, CH3COH. The carboxylic acid has 2 carbons is the acetic acid, is a component of vinegar. And then you have the sodium acetate. So let's say that I have a mixture of these two in a solution, and I come in and I add some acid, for example, HCl or nitric acid, which ionizes completely and produces, a surge of hydrogen ions. Well, because you have this base in here, right? Because you have that base in there, what's going to happen is that base is going to absorb the extra hydrogen ions that the strong acid brought in, and it's going to neutralize them. and generate some extra acetic acid. If, on the other hand, you add a strong base, let's say, for example, I come in with some, I don't know, some sodium hydroxide or something like that, well, what's going to happen then is that the acid component of my mixture is going to absorb those hydroxide ions, react with them, and the product of that will be neutralizing the hydroxide ions, and you'll have water and the back to the acetate. So essentially, that is how a buffer solution works. All right, a buffer solution works by resisting changes in pH, because either one of the components of the buffer system is able to react with any incoming hydrogen ions or incoming hydroxide ions. You can watch this on a graph. If you take, for example, HCl and you add it to this acetic acid and acetate mixture, you can see that if you simply add the acid to water, you can see where the pH drops very quickly, very dramatically. However, when you have a buffer solution, you can add quite a few moles of HCl and the pH remains stable, as you can see there, right? You can see the stability here. All right. So that's what a buffer does. All right. So there's a couple of things that I want us to practice. Number one, we need to be able to recognize if a given solution is going to work as a buffer system. And then we want to do some calculations. Okay, what would be the pH, or things like what would be the proper, how would you build a buffer system with different components? All right. So ready? Okay, so here I have three proposed buffer system. A is potassium fluoride and hydrofluoric acid, KF and HF. The second one is potassium bromide and hydrobromic acid. And the third one is sodium carbonate and sodium bicarbonate. And just to help you out, you can see there the descriptions of each one of these components. And so I want you to think about it for a moment. Let me know if you're kind of like not kind of like understanding what we're supposed to do here. What we're going to say is, if I mix those two substances in a solution, would I be able to get a buffer system just based on the identities of these things? Okay, no, forget about molarities and stuff like that, just based on their identities. All right, so let me give you a few seconds to think about that, and then we'll scroll down one by one. So the first case, we have HF as a weak acid and fluoride is its conjugate base. So would that work? Answer is yes, that will work as a buffer solution, because by definition you have the weak acid and its conjugate base. Let's look at the second one. You have HBr and KBr. But HBr, hydrobromic acid, is a strong acid. Remember, that's one of the ones that you're supposed to memorize. So does that work as a buffer solution? No, it's not going to work. Not a buffer solution, because you cannot build a buffer solution with a strong acid. The strong acid is going to ionize completely, whether there are bromide ions or not in the solution. Okay, third one. It tells you here that carbonate ions are a weak base, and the bicarbonate ion is its conjugate acid. You know what? I could have said it a different way. I could have said the bicarbonate ion is a weak acid, and carbonate ions are the conjugate base. So would that work as a buffer system? Yes, it will. It will work because you have precisely the components you need. As a matter of fact, this is part of the system that allows our bodies to control the acidity of blood and keep it slightly basic, slightly alkaline, 7.3, 7.4, something like that. And a lot of it has to do because, remember what we talked about earlier, that this bicarbonate ion can be sourced from CO2 in the atmosphere. And remember that we breathe out CO2, right? It's part of our metabolism. So let me give you, this is not on your slide, but let me ask you this. What about this? What about if I had a solution that has HF and sodium carbonate? You might say, well, HF is a weak acid and sodium carbonate is a weak base. Would that work? Wouldn't work. They are not conjugates of each other. In other words, they are not going to establish that equilibrium, right, with the common ion effect to establish a buffer solution. All right, so be careful. Again, several things to think about here from the previous chapter. Number one, you've got to be able to recognize when they give you a formula if it's a strong acid or not. Secondly, you've got to be able to tell based on the number of hydrogens in one component or the other one if the pair that we're giving you is a conjugate pair or not, okay? So those are kind of skills that I want you to pick up as we go along. Okay, so this is one of the skills you need to develop is recognizing whether a given system will work, excuse me, as a buffer or not. Okay, the second one is doing calculations. What I want to do now is I want to build a buffer and I'm going to see what happens when I try to change the pH of the buffer. So here is our buffer. We have 0.30 molar ammonia with 0.36 molar ammonium chloride. And then we have what is the pH after the addition of 20.0 milliliters of 0.050 molar NaOH to 80.0 milliliters of the buffer solution. All right, so let's go back here to our, pull out of this screen here. I'm gonna bring us back to our camera. Oops, that's the wrong one, sorry. There we go. There we go. All right, so that's what we're talking about. Now, the first thing is, notice that the way I set it up is I set it up in the direction of the ammonium ionizing into hydrogen ions and ammonia. I could have done it the other way, but remember, if I want to use the Henderson-Hasselbalch equation, right? I want to use the Henderson-Hasselbalch equation. We said that it gives me the pH is the pK plus the log of the molarity of the base divided by the molarity of the acid. The reason why that works is because I have the equilibrium set up such that the base is on the product side and the acid is on the reactant side. So I always want to write this equation in the direction that yields hydrogen ions. Remember, if I were to write this, so let me do a little sidebar here. If I were to write this in the other direction, from the direction of ammonia, reacting with water, the products would be, yes, ammonium ions, but the other product is actually hydroxide ions. So that means that I would be doing calculations where I had to kind of like turn things around. And instead of calculating pH, I'm calculating like POH and something like that. It's probably not worth our effort. So I recommend that always write the equation in the direction of the acid ionizing into the base, okay? So that's the way it works. So pH would be pK. And remember, this would be the pKa of ammonium ions plus the log of NH3 molarity over NH4 plus molarity. So we need to find out what's the pKa of the ammonium ion. Well, let's see. Let's go to our famous table here. Here are the Kas. Let's see if we can find the ammonium ion in here somewhere. I guess not. So what we're going to have to do then is we're going to have to come back here and say, you know what? I'm going to have to calculate Ka of ammonium ions by using that formula, product of water divided by the Kb of ammonia, right? So that's 1.00 times 10 to the minus 14 divided by, okay, let's see what the Kb of ammonia is. So what we had to do is, instead of coming to this table here of Kas, we want to go to the one that has the Kb values. And this one gives me ammonia as 1.8 times 10 to the negative 5. All right. So let's go there. Come back here. So this would be, oh, what did we just say? 1.8 times 10 to the minus 5. So let's see what that is. Ten to the minus 14 divided by 1.8 to the negative 5. And that's like 5.6 times 10 to the minus 10. Cool. All right. Now we had to get the pH. So pH will be pK, which would be minus the log of that number we just wrote there, plus the log of the ratios of molarities. Okay, ammonia in this case is 0.30 molar, and ammonium is 0.36. All right, so I'm gonna go ahead and take the ratio here. So, well, I can do this in any order of steps in here. I'm sorry, guys. So let's go ahead and do it here. So 0.3 divided by 0.36 equals that. I know that's going to be negative when I take the logarithm of that because it's less than 1. So I'm going to put that in my memory. You know what? Let me try that again. Make sure that I got it right. 0.3 divided by 0.36. Take the log of that. Put it in my memory. And now I have 5.6 to the minus 5. And I had to take the log of that, but that's the negative of it because it's minus the log, that's pK. And then I'm going to add what I calculated in memory, and I get, what did I do here? I think I did this wrong. Hold on a second. 5.6. Oh, I know what happened. I did 5.6 to the minus 5 instead of to the minus 10. Sorry, my bad. Now we're going to take the log of that. There you go. And now we're going to add what we had in memory. And it comes out to about 8.58. I think that's wrong still. Let me try that again. See, guys, I have the same problems you guys have. Okay, I want to get 0.30 divided by 0.36. That's that. And I'm going to take the log of that. All right. And I'm going to put that in memory. And I'm going to take 5.6 to the minus 10 to the log of that, make it positive, add what I had in memory. Okay, that's the value that I should have gotten. It's 9.17. All right, so that's the starting pH of our buffer. Okay, that's the starting pH of our buffer. Now, the question now was, what is going to be the pH after I add 20 milliliters of NaOH to 80 milliliters of the buffer solution? Okay, so this is where I start. So if you guys go to your next slide, you're going to see something that looks like this, correct? So you got to be careful because you had to consider what is the final volume of this solution, right? So we started out with 80 milliliters of our buffer plus 20 milliliters of NaOH. So we have 100 milliliters total solution in here. So when we do our reaction here, remember this is a buffer system. So the idea is that if I'm adding base here to compete, the component of my system that's going to try to counterattack that will be my acid component, which is the ammonium. So the reaction that's going to happen here is this one, all right? So what I want to see is when that happens, how much ammonium is going to be left and how much more ammonia is going to be generated at the end, okay? All right, so let's see what our initial molarities are. First of all, let's start out with the initial here. Let's start with the hydroxide ion concentration. So we're going to use our famous, remember the dilution formula, M1V1 equals M2V2. And essentially, we are solving for what is the molarity at the end of the dilution process. So this will be, I added 20 milliliters at a molarity of 0.050. And it's diluted now in a final volume of 100 mLs. All right. So that gives me 0.010 molar. So basically, I just diluted this by 5, basically is what happened. Okay, so that's where I'm starting here. So that's my starting molarity here, 0.10. Okay, let's see what our ammonium concentration is at the start. So that would be, there's 80 milliliters of buffer. Remember the ammonium concentration was 0.36, right? And I have a final volume of 100 milliliters. Yeah, cancels out the milliliters. And this is going to come up after rounding and stuff. It's going to be dropping to 0.29. You know what? If you guys decide to round it to 0.30, that's fine. So I'm going to put this at 0.29. And my initial concentration of ammonia, again, was 80 milliliters of buffer. But remember that the ammonia itself was 0.30 molar. In a final volume of 100. So again, that's like 4/5, like 80% of this, which is, pretty much 0.24 molar. So that's my initial concentration of ammonia, all right? So that's where we're starting. And so what we need to do now is we need to carry out the change. Now, in this case, we don't have an unknown. We know that this is going to be completely reacted. In other words, it's a strong base, it reacts completely. So we're going to be removing all of that extra hydroxide here. And of course, that's stoichiometrically what the change is going to be in the ammonium concentration. And that's what's going to be added to my ammonia concentration in there. So let's do the math here. You can do that without a calculator. This will be 0.28. This will be 0 left over here. And this will be 0.25. All right. So in other words, ammonium is 0.28. Ammonia is 0.25. And now we're going to use the Henderson-Hasselbalch equation. Yeah, remember we had to do this first before we could put in the initial concentrations in there. So this would be pK, which we already established earlier was 9.25 plus the log of the new concentrations that we have now. So that'll be 0.25 over 0.28. All right, let's see what that is. 0.25 divided by 0.28 equals that. We're going to take the log of that, and we're going to add 9.25, and we get 9.20. So we had started with a pH that was 9.17. We added essentially 20 milliliters of base to this, and the pH barely changed, about 0.03 of a unit. Very, very small change. Small change. Okay. So that is essentially so you can see how to solve these kinds of problems. Let me leave it there for a few more seconds. Don't forget that after we finish here, I will be scanning these sheets and then I'll post them along with the video of the lecture. All right. Any questions, anybody, either by chat or you can unmute your phone, your microphone and ask. Let me know if you're good. Yeah. All right. Let's do let's see if we can do at least one more problem here. All right. And it's actually your next slide, I believe. Let me see if that's correct. Let me come over here to the screens again. Where are we? Okay, we were doing this. Just did this guy, right? Yeah, I had it in here, but I just did it by hand because I figured it'd be much more easier to follow. Okay, so here's the next question. You have the following reagents: carbonic acid, H2CO3, sodium hydrogen carbonate. Hydrogen carbonate is the way that, real chemists, not like me, call, bicarbonate, HCO3, and sodium carbonate. Okay, so how would you prepare a liter of quote unquote carbonate buffer at a pH of 10.10? So the idea here is, what is the strategy that you follow here? So let's go back to our screen over here. Let's consider the strategy. So the idea here is, I want to find a system consisting of two of these components that are conjugates of each other, such that it'll be close to that pH that we want. In other words, the goal would be to find a conjugate pair with a pKa that is as close as possible to the pH that you desire, the pH desired, right? In other words, what you're saying is, if I have a system and I can put, the same amount of each one of the two components, pH would be essentially the same as the pK, and that's what I'm looking for. So in this case, we have two options. So what are my options at this point? I can do either a system that consists of carbonic acid, which ionizes to hydrogen ions and the bicarbonate ion. And then I have another system that would have the bicarbonate ion that ionizes to hydrogen ions and the carbonate system. Notice that this is a diprotic acid, so essentially we're looking for the Ka1, right, and the Ka2. So this system would consist of the carbonic acid and the bicarbonate. This system would have bicarbonate and carbonate. Remember, they have to be conjugates. In other words, they have to differ by no more than one hydrogen from each other. All right? So let's find out what the Ka of this guy is. I'm just going to write down some numbers. I don't know if these are going to be absolutely correct, but you know what? Actually, let's look them up. We have time. We have about 10 more minutes over. Let's go ahead and look it up. Let's go back here to our tables that we did before. And I guess the one we're looking for is the Ka values. And we were looking for the, first of all, the H2CO3. Well, they don't have it here. Oh, you know why? Because it's a polyprotic. Here it is. Carbonic acid, 4.2 times 10 to the negative 7. And bicarbonate, HCO3, would be 4.8 times 10 to the negative 11. All right, so I'm going to come back here to our paper, and I wrote them down already. So we're saying that this system has that value of Ka, this one has this value. So let's find out which of these will work. So we have to find out what would be the pKa for this guy, and what would be the pKa for this guy. All right, so let's go ahead and find those out. I think I'm losing the screen again. I'm losing my internet connection. Okay, I might be getting disconnected here. I'll be right back. Hello, hello, hello. Hello, hello. Okay. All right, sorry guys, I'm having some technical difficulties today. I hadn't had this problem before, but hey, here we go. So hopefully I didn't lose you here. I was able to get back in. I was going to do what? Oh, we were here. Okay, we were here. Okay, so we were going to calculate the pKs. So let's see, 4.2 to the negative 7. We're going to take minus the log of that, and that's 6.38. And for the other guy, it would be 4.8 to the negative 11 minus the log of that is 10.32. All right. So the idea here is that if we want to choose, if our target pH is 10.10, which of these two would work better? Which one is closer to the target pH? Right, it would be this one here. Right? That would be the one. So, oops, sorry, target pH. So we're going to use this system. Now let's find out. I'm going to make a liter of this. So what I need to find out is, well, since this is not exactly the pH, I need to adjust the ratio of base to acid so I can get the exact pH I want, right? So let's go ahead and do that and probably wrap it up at this point. So, I'm sorry. So we have 10.10 equals 10.32 plus the log of the base, which is CO3 minus, CO3 2 minus, I'm sorry, over HCO3 negative. So what I want to find out is, well, what is this amount? And that would be 10.10 minus 10.32, which equals 0. Oops, sorry, it's going to be a negative, right? So 10.10 minus 10.32 equals negative 0.22, right? So if that's the log, then that means that the actual ratio, oops, let me put this up a little bit. The actual ratio of these two would be 10 to the minus 0.22. So I'm going to pull my calculator in again, and I'm going to find what is the one that I use here. Again, your calculator might have to do this a little different. So basically, this comes up to be 0.60. Now remember, this is a ratio, correct? This is a ratio. So I'm saying that the concentration of sodium carbonate is going to have to be a little less than the concentration of bicarbonate. So let's propose a possibility. For example, let's say that I want to say, possibility. Let's say that I want to make my concentration of bicarbonate, let's say I want to make it, let's say 0.5 molar. So that means that the concentration of the carbonate ion would have to be 0.60 times 0.5, which is 0.3. So the key here is I had to make a solution that will be 0.5 molar in sodium bicarbonate and 0.30 molar in sodium carbonate and in a liter, and that should give me a solution that has buffering capacity around pH 10.10. All right. So that's how you solve these kinds of problems. All right. Okay. I think we're out of time at this point. So let's come back here. Let me see if anybody has any questions. Let me check the chat here. We lost the chat block again because of the disconnection. Again, I apologize, guys. I hadn't had this happen in our previous sessions, right? Actually, I think we did happen one time. We slightly got disconnected. I think as I've mentioned, you probably have the same experience in your homes. I don't know. My internet gets a little bit sluggish between, after 4:30 ish and all the way till about, 9 o'clock or so. So that's why I'm located over here. I put myself here in the dining room, which is next to where the Wi-Fi is. But even so, I mean we call it the router. Even so, we still got some issues here. All right. Okay, let me see if you have any questions. Just you can unmute your phone and ask, or you can put a message in the chat. Any questions? Doesn't have to be about this. It could be about anything else.
I had
No.
a question.
I hear a voice.
Oh, can you hear me? Oh, it's Sarah. I don't know if you can hear
Sarah,
me.
yes.
Okay. So the possibility, the 0.50 molar and the 0.30 molar, was that just like random numbers that you?
Yes, totally.
Okay.
Totally.
Okay.
Yeah, I could have said 1 molar HCO3 and 0.6 molar in the other one. Yeah, I could have done it that way. Yeah.
Oh,
Thank you.
okay. Okay. All right. Thank you.
So yeah, let me highlight that. That's a possibility. I'm just shooting for. I picked those numbers because those are typical types of molarities for buffer solutions. Uh, I mean, there's a lot of other buffers. I mean, like I said, if you read in the text, there is a really good explanation of how the pH of the blood is kept around what we call physiological pH, 7.3, 7.4. Maybe we'll talk about that when we come back from spring break. I don't want to overload you guys with information. All right. So today we learned about several things, right? We learned. Oh yes, Asade.
Hi, everybody. Hi, Professor.
Yeah, can you speak up, please?
Yeah, for our exam, how we can write all this, because our exam is going to be multiple question or?
Like I said, I have exactly 0 plans for exams right now because I don't know how to do it. And several faculty members are kind of researching this and how we're going to do it. So that's why I haven't scheduled any of them. So
Thank you.
don't worry about it for now.
Thank you.
No, thanks for asking. Appreciate it. Okay, any other questions?
Also, the whole point of the question is to get like what you think the possibilities would be for the molarities. Like that's the goal that you're trying to find.
In this question that we did just now?
Yeah.
Yeah, the problem really goes, I mean, I took it a little farther than probably it needed to be. Because the question was simply, how would you prepare a liter, right, of this thing? Let me pull this down here. How would you prepare a liter of this? And what I wanted to, impart on you was a strategy that the idea is you have to choose which pair of these 3 components, which of them would make a conjugate pair with the right pK. That's pretty much what it is. Now, once you get there, you have to still decide, well, what has to be the ratio of base to acid in there? And I just gave you an example in there.
Oh, okay. So you're just like looking for the
Really,
ratio.
you would end it here after you find the ratio of base to acid, because after that is more of a, experience in what kinds of molarities you're going to be working with and that kind of stuff. Okay. Yeah. Thanks for asking.
Oh, okay.
All right. Any other question? Okay, so what we picked up today was that when you have a solution that contains both the weak acid and its conjugate base, the ionization of the acid is suppressed, and you establish an equilibrium, which is essentially an example of the Le Chatelier principle, where each one of them keeps the other one in balance, in check. And so if you add excess acid and therefore kind of like cause one side of the equation to kind of get heavier, the response is that Le Chatelier tells us it's going to come back the other way. So the excess acid is going to be consumed. In the same way, if you add base, which is equivalent to essentially adding hydroxide ions or decreasing concentrations of hydrogen ions, then the reaction then is going to have to go in the other way just to establish equilibrium again. And we take advantage of essentially what is a Le Chatelier principle example to build a solution that is what we call a buffer or a buffer system, where we deliberately prepare the solution to have a target pH and resist changes in that. You know, in biochemical systems, this is very important because those catalysts that we talked about at the beginning of the semester, those enzymes, they typically require a specific pH for maximum activity. And so it's important many times for the cells or the tissues or, you know, your system in your body to be able to regulate the pH and deal with any sudden changes in the acidity. Okay, so that's what we learned. And we learned then the Henderson-Hasselbalch equation that we use for calculating either the pH of a buffer system or what should be the proper ratio of base to acid, or which weak acid and conjugate base system would work to build a buffer of a target pH, okay? So that's all we got for tonight. And as you take off for your spring break, I hope that you guys get some time to relax, to rest a little bit. I realize that for many of you, that's almost impossible. Those of you who have kids at home, my heart goes out to you if your job situation has been compromised or anything like that, or if you're taking care of a loved one. Hey guys, we're all in this together, and my hope is that we'll make it through. And as far as I'm concerned, I really want to make sure you guys succeed and you can move forward and kind of try to minimize the stress. Okay, so have a great spring break. I will be sending out messages, so keep monitoring your Canvas announcements because I will be sending some more messages. Some of them are not from me. They'll be from the administration of the university as they kind of deal with plans and stuff like that. So make sure that you're on top of things and you don't get caught by surprise when you return from spring break, okay? So we'll see you in about, 10 days or so or something like that. I will send out the connection information for our next session. And my goal is that by then, we will have both a lecture time and also a dry lab time. But I got to work on it. Okay, guys? So have a great spring break. Tell you what, I'm going to stick around a few more minutes just in case somebody has any remaining questions. But I am going to pause the recording now for the benefit of those who are going to be taking the recording.